Alright everybody, we're going to be talking about some infinite geometric series. Below I've got two examples of what a geometric series means. And then when you have this dot, dot, dot at the end, it means it's going to go on for a while. And so just a few things to remind you of what makes a geometric series. When each subsequent term is multiplied by a number to get the next term, and you have a pattern. So again, if I'm timesing by 2 here, each term you can get by timesing the previous by 2. That multiplier we actually call the ratio. And here, not quite as obvious, but if you divide by 2 or multiply by 1/2, multiply by 1/2. If I multiply by 1/2 again, you get a 3/4, and then this could go on for a while. Anytime you have this multiplication pattern, it's a geometric series. Sorry about that. And as it turns out, if you have an R value that is between 1 and -1, then you can say that the sum, or I should say the infinite sum, sorry, I'm getting used to this. Not only does the infinite sum exist, but we're going to translate this into the fact that it converges. And that's going to be kind of the one of the buzzwords at the end of this year. And so if we talk about this first example up here, R is 2, and 2 does not fall in this inequality. And if you just keep thinking about these numbers, 32, 64, the idea is if I really start adding them all up, that sum is just going to get bigger and bigger and bigger. We would actually say that this diverges. The sum goes to infinity. But down here, if you continue this pattern, 3/8, 3/16, just generally speaking, these fractions are getting smaller. Visually speaking, if you added these together, 6 plus 3 is 9. Then if you add 3/2, you're at 10.5. Then you add 3/4, you're at 11. And then you start adding, these fractions. The idea is, does it level off? Does it approach a sum? Are you eventually adding fractions that are so small that it's just like you're adding, almost nothing? And also, if R, down here, R is 1/2, and 1/2 falls in this range, so the idea is it will converge. I want to introduce some notation that's gonna show up. Maybe this is review, maybe it's not. But when you have a geometric series, sometimes we represent that in an equation in the form of a sequence. And the general form is a1 times r to the n-1. Maybe it looks familiar, maybe it doesn't. This a1 represents the first term, and the r represents the pattern. The common ratio is what they call it. So if you wanted to represent this series right here, you could represent it with a 6 times your r to the n-1. And the idea with the expression is that if you wanted, for instance, the third term, it would be 6 times 1/2 to the, again, there's my 3, there's my n, 3 minus 1. You have 1/2 to the second, which would be 1/4. So you have 6 times 1/4, which is 6/4. Oh my goodness, too much work. 3/2 is the third term. So it's kind of an efficient way to represent that. Again, just to make sure you got it, the equation up here would be, what would it be? The first term is 1, r is 2 to the n-1. you getting familiar with looking for this geometric structure is important, because a lot of times if you wanted to know what the sum is, or if it has an infinite sum, scroll down a little bit, you're going to see this equation show up with a sigma. So in English, this means what's the sum from n equals 1 to infinity of some expression. So again, you might see it like that, or you might see it with the actual expression plugged in. And so it'd be really nice if you can say, okay, it's asking me for a sum. This guy right here is the r, this is the a1, and I know it's geometric, and I know the r is less than 1/2, so I know it converges. And there's a formula. For a geometric series, if r is in that interval, then the sum will be the first term divided by 1 minus r. So, if I apply that to this example, a1, 6, r is 1/2, so I have like a 6 over 1/2, which is equal to 12. So the infinite sum, which is also the number it converges to, it's also where the horizontal asymptote would take place, or the infinite limit, so there's lots of vocab words in here, would be 12. And that kind of makes sense back here when we start doing it by hand. It's 11 plus some fractions, so it's going to start leveling off, and it actually levels off at 12. All right, let's put you to the test. Let's do a couple examples. So the question that usually comes up on the national exam is, it'll give you just a quick series, and it'll say, do the following converge. And the idea is you're able to look at these and identify that they're geometric, and then if they do converge, so if the answer is yes, what number do they converge to? So we're going to do these quickly, and if I go too quick, listen to it again or try it on your own. So, all right, sigma means we want the sum. Infinity means we want the infinite sum. And then ideally, you want to look at this and say, well, it's got this form of a geometric with my a1 and my r. More specifically, the r is a proper fraction. That r is between -1 and 1. So, drumroll please, this will converge. Sloppy. There we go. Same thing here. It's geometric. This is a1. This is r. 1/5 is between 1 and -1. So, you guessed it, it will converge. This last one, again, a1. This is r. In English, this means the pattern is it's tripling. But, 3 is greater than 1. Will not converge. Yeah. So quickly we can determine if it converges or not. And sometimes that's all you're asked. But if it's geometric, we also have the formula. What number will it converge to? And so if we use the formula, the number it converges to, if it's geometric, can be found by doing a1 over 1 minus r. Careful with that double negative in there. So we've got 1 plus 1/3, which is 4/3. So I think this is going to be, 2 times 3/4. So we got like a 6/4. Same thing down here. If we want what will it converge to, so again, it converged to 6/4. We've got a1 over 1 minus r. We've got -10. And then we've got like a 4/5. So we've got a -50 over 4. I hope my math's right. And again, why is it negative? Well, in this case, we'd be adding the sum of a bunch of negative numbers. This one does not converge, so we have nowhere to go. All right, food for thought. All right, let's end with this question. Where are we heading? Well, not every series is going to be geometric. Geometric behaves nicely. They have sums. Sometimes the question will just be, does this converge? And you'll be given a series or asked about a series that isn't geometric. And we're going to have to figure out ways to answer that. And so this is a classic series I'll let you think about, and I'll make a video soon enough about it. But this series, if you plug in 1, you get 1 over 1. If you plug in 2, you get 1/2. If you plug in 3, you get 1/3, 1/4, on forever. The big question is, will that converge? And we'll answer that soon enough. Thanks for tuning in.